Today we're beginning our chapter about circles. So we're going to begin with just a basic overview of circles, and we're going to introduce a special part of a circle called a chord, and we're going to look at some theorems that have to do with chords. So we're going to review points associated with the circle, identify and prove relationships in theorems for congruent circles, and then also chords. So in a circle, in circle C, the center is point C. So remember, you name the circle after the center. So if this was an A, then you would say this is circle A with the center A. So the center point is how you name your circle. So you would, if I would say, what's the name of the circle? You would write circle and then the letter of the center. And then the center is always a point, right? So if I say, what is the center? You'll say, it's point C. And then you have the segment CX as a radius. So here's C and here's X. So the radius goes from the center to a point on the circle. So this is a radius. And so if I say, name a radius of the circle, you can say segment CX. And how do we write a segment? Well, we write the 2 points, and then we draw a line above them with no arrows to say that it's a segment. So there's different radii here. There is the radius CX, that's the one that we pointed out already, but notice that segment CR is also a radius, and segment CQ is also a radius. So remember, a circle actually has an infinite number of radii. Then we have another special segment, LM. Now, LM is called a chord. So a chord are 2 points on the circle that are connected. So there have to be points on the actual circle. So a radius went from the center, which was not on the circle, it's in the middle of the circle, to the circle. A chord has to be 2 points that are on the actual circle. So a chord is a segment, so we're going to use the notation for a segment. We use the 2 points with the segment line above it. So you use the 2 points that are on the circle, LM. And then we have another segment, the segment QR. So the segment QR is actually a chord because it has 2 endpoints that are on the circle. But it's a special chord because this chord actually goes through the center and then ends up on the circle as well. So this is what we call a diameter. A diameter is a special chord that goes through the center, but both of its endpoints are still on the circle. And then the last part of the circle that we're going to look at is called an arc. So an arc is the 2 points, but you're connecting them on the circle. So LM, we would consider an arc. LM is an arc. And so we name an arc by naming the 2 points that we want to look at, or the space in between them that we want to look at. So we put those 2 points, and then we draw an arc above them to show that we're actually looking at the arc. So notice the difference between the LM chord. So that one is a straight line connecting those 2 endpoints, and the arc LM is connecting those 2 points using the circle to connect them. All right, so now that we reviewed parts of a circle, let's go ahead and talk about what makes 2 circles congruent. So congruent means they have the same measure. So congruent circles are circles whose radii are congruent. So as long as 2 circles have the same radii, the same measure of radii, that means their radii are congruent, then that means that those 2 circles are congruent. All right, so we have our first postulate for this chapter, and it is called the chord postulate. So the chord postulate says that if a line intersects the interior of the circle, that means inside the circle. So if a line goes through the circle, then that means that that line contains a chord of the circle, which makes sense because if it's going through the interior, then that means that it has 2 points on the circle, which that's the definition of a chord. Our next theorem says that in a circle, if a radius is perpendicular, which means that it's a 90-degree angle, to a chord of that circle, then it bisects that chord. Remember, bisects means it cuts it in half. So what that looks like is, here's our radius, right? And that radius is perpendicular. So the radius OC is perpendicular to the chord AB. It's perpendicular at point D, so it makes a 90-degree angle right here. So the theorem that we just talked about says that since our radius OC is perpendicular to our chord AB, then that means that it has bisected or cut in half the chord AB, which means that AD, this part of our chord, has to be equal to this part of our chord, DB. So if this measure was 5, then this measure would also be 5. They would be equal. Which also means that we have some equilateral triangles. So in a circle, here's our next theorem, in a circle or in congruent circles, if two chords are the same distance from the center, then the chords are congruent. So what that is saying is that if you have two different chords and they're the same distance away from the center, then the length of those chords are also the same. So for example, let's say that we know the distance from A to X is the same as the distance from B to Y. So that means that the chords are the same distance away from the center. Then that means that the chord QR is the same measure as the chord PN. So let's say that the segment AX, let's say that was 4. Right? And let's say that BY was also 4. And we're like, oh, that means that they're the same distance away. They're both 4 away. Then that means that if the chord QR had a length of 7, then that means that the chord PN would also have to have a length of 7. Our next theorem that says in a circle or in congruent circles, if two chords are congruent, then they are the same distance from the centers, which means that it goes back and forth. So that means that if we know that QR is 7, the chord QR is 7, and we know that PN is also 7, then that means whatever distance AX is, then BY has to be that same distance because the chords are the same.